Hey guys, so before we dive too far into chapter 9, we wanted to address something pretty important. So we're going to start looking more and more at these free response questions, and a big part of that is going to be including an explanation of your answer, which means we have to talk about units in calculus. All right, so throughout the next chapter, we're going to be applying our calculus ideas to real world applications. For most of the questions you will be asked, you will be required to explain the meaning of your answer in the context of the problem using the correct units. So this is going to be a huge thing that when they grade your AP exam, they're going to be looking for is, can you explain the answer you got? Not just did you get the right number, but can you explain the answer you got correctly and using the correct units? So when you do these explanations, there's kind of going to be three parts to it. All right. When you write an explanation, the first thing you're going to want to make sure you include is what you measured or calculated. All right, and then the second part that you are going to have to include is a description that uses the correct vocabulary. Or the appropriate vocabulary. All right, and then the last part of this is going to be the value that you found with the correct units. So really, getting the right answer, the right number, is only one part of this explanation. All right, so we're going to look at what this looks like in problems using derivatives and in problems using integrals. So when we find a derivative, we're finding the instantaneous rate of change. Or in other words, we're finding the slope. And a lot of times these derivatives, that's what we call, they always have this rate. All right, even the slope of the tangent line, right? It's the rate of change. All right, to determine the appropriate units for a problem where we use a derivative, it's helpful to think of this as a ratio. So remember, we know that slope is really just the rise over the run, and you guys have been doing that since algebra. All right, slope is always this ratio. So let's see what this is going to look like in these problems. This first one we're going to do is going to be without a calculator, and then the second one we're going to use our calculator to remind ourselves how to find derivatives using the calculator. So the height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. So use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. So the first thing we have to recognize is that we are doing an estimate here. We're not finding the exact value for h prime of 6 because we don't have a function. All right, but we know that when we see h prime of 6, that's a derivative, it means that we're going to need a slope. So if we had the function, we take the derivative and we would substitute 6, but we don't have that. So instead, we're going to have to think about how we can actually find the slope. So we know that the first part of our problem here, we're going to have to find the actual answer. So h prime of 6, the only way for us to find this slope is actually going to be to find the slope between 2 points. So we know that 6 is between 5 and 7, so we're going to use regular old slope. So h of 7 minus h of 5 over 7 minus 5. All right, let's see, h of 7 is 11, so 11 minus h of 5, which is 6, over 2. And so we get an answer of 5 over 2. All right, now we have to think about what these units are. Well, we put our y values or our h of t values on top, and those were measured in meters. And then the bottom value, that was our time, which was in years. So this is meters per year. All right, now the second part of this is actually the explanation, and this is really the more important part that we need to worry about right now. So we need to figure out what this is that we actually just measured. Well, we were given the height of the tree at time t, all right, and then we had to find the slope. So what we did, or what we found, was the height of the tree and we know that this is the rate at which it is changing. All right, so because the height is changing throughout time, and we found the slope of it, we know that we're finding the rate at which the height of the tree is changing. Well, since this is a positive slope, all right, we know that when we look at the first derivative, it tells us whether the function is increasing or decreasing. So the height of the tree is increasing because this is a positive number. So it's increasing at a rate of, and now we need to include our value. So what we've done is we've talked about what we measured, so the height of the tree. We talked about what's happening to it. It's increasing at a rate of, now we need to include our value with our units. So the height of the tree is increasing at a rate of 5/2 meters per year. Move that down so you guys can see. Sorry. So those are the three things that we need to include. What is it that we found? What's happening to it? And then what is the actual number with the correct units? So the height of the tree is increasing at a rate of 5/2 meters per year. Okay, let's look at the second one. When a certain grocery store opens, it has 50 pounds of bananas on a display table. Customers remove bananas from the display table at a rate modeled by this function f of t. F of t is measured in pounds per hour, and t is the number of hours after the store opened. So before we do anything, I want to figure out exactly what this function is telling me, right? We knew in the last one, h of t was measuring the height of the tree. Well, in this one, f of t, it says that customers are removing the bananas from the display at a rate modeled by f of t, which means f of t is the rate that customers remove bananas. All right, f of t is measured in pounds per hour, and then t is in hours after the store opened. So that's going to be important too, though, to know what f of t is measured in, and then what time is measured in. So we want to find f prime of 7, and then using correct units, explain the meaning of f prime of 7 in the context of the problem. So again, we know that we're going to be finding a derivative. Now for this one, I don't want to find that derivative by hand. So we're going to go to our calculators, and we're going to refresh our memories on how to find a derivative using our calculator. So if we hit math and we go to number 8, we can take a derivative. So we're going to take the derivative with respect to x, and we're going to type in this function. So 10 plus 0.8x sine of x to the third divided by 100. And we want to find it at 7. So we want x equals 7. Ooh, before I do this, I'm going to check and make sure. Okay, I'm in radian mode. Make sure you are too, because otherwise we're going to get different answers. There we go. Awesome. So we know then, so this first part is to calculate our actual value, right? So f prime of 7 is going to equal, and we want to round to 3 decimal places here. On the AP exam, that's always going to be your standard. So we have to be careful here because it's 0.1195, which means we really need to make this negative 8.120. All right, and now we need to actually pay attention to our units here. So when we took this derivative, we did f of t over t. So we did pounds per hour and then we did per hour. Now, I kind of skipped a part up here where we talked about position, velocity, and acceleration. Sorry, I don't know how I missed that. But if you remember, when we did, I'm going to jump up here for 1 second, change gears for 30 seconds, my bad guys. When we did position, velocity, and acceleration problems, we know that the derivative of position is velocity, the derivative of velocity is acceleration. Position is usually measured in meters, velocity is usually meters per second, and then acceleration is meters per second squared because it's meters per second per second. So if we want to, when we name this with units, we could say pounds per hour squared, and it's kind of similar to having the acceleration. It's not because this isn't an acceleration problem, but in terms of the units, we could write it as pounds per hour squared if we wanted to. All right, our second part then is this explanation. So we found the number, but that's only half the battle when we do this. So again, we need to talk about what we measured, describe it using the correct vocabulary, and then name the value with the units. So we know that f of t was looking at the rate that customers remove bananas. So that's what we measured. The rate at which customers removed bananas. Oops, might help if I actually spell customers correctly. The rate at which customers removed bananas. And then let's see, what was that doing? Well, this is a negative slope, which means the rate at which the customers removed bananas has to be decreasing because of this negative sign right here. So the rate at which customers remove bananas is decreasing at a rate of, and now we can actually put our number. So again, what we measured was the rate at which customers removed bananas. And because we took a derivative, we figured out it was decreasing at this specific rate. Now, when you include your number here, because we already said that it's decreasing, we don't want to put a negative sign with our number. So it's decreasing at a rate of 8.120 pounds per hour. Per hour. If you put a negative sign with it, then you're saying it's decreasing at a negative rate, which would really mean it's increasing. So you want to be careful about that kind of thing. All right, so again, looking at derivatives, we were finding these rates of change or the slopes. So everything we'd said was either increasing or decreasing depending on if it was positive or negative. And it was increasing or decreasing at that rate, and then we had the units to go along with it. All right, so now we're going to look at what happens when we do this with integrals, because this is the new thing we're doing, right, is dealing with integrals. So when we find, this should say an integral, we're finding the area between a curve and the x-axis. To determine the appropriate units when we use an integral, it's helpful to think of this as, this should also say n, area. So I want you guys to think even just of like a, let's do velocity, a velocity graph. So if we have the velocity, let's say we're measuring this in units, this would be meters per second, and then time would be in seconds. So if we think about an integral, it means that we're going to be finding the area that's trapped between the curve and the x-axis. So that means we're going to be multiplying the base times the height, which means we're going to take meters per second and we're going to multiply by seconds. And so the seconds cancel and we're left with meters. All right, and that's what's always going to happen when we do an area, is it's the base times the height, so we multiply the units there. All right, so these are both calculator questions. Number one is really only a calculator question to help us with some of the arithmetic, not because it's super difficult. So let's see what we're given here. Water is removed from a tank at a rate modeled by R of t in liters per hour, so that's important, where R is differentiable and decreasing on 0 to 8. Selected values of R of t are shown in the table. At time t equals 0, there are 50,000 liters of water in the tank. So we're given this R of t, which is the rate at which the water is being removed, and then we've got the time. So we want to use a left Riemann sum with 4 subintervals that are indicated by the table to estimate the total amount of water removed from the tank during the 8 hours, and give your answer using correct units. Now you'll notice this one doesn't ask you to necessarily explain your answer because they kind of already told you what you're finding. You're finding the amount of water that's removed from the tank during the 8 hours. So they kind of gave away all the important stuff for the explanation. So in this one, they're really just asking for the numbers. So if we're going to do a left Riemann sum, we're going to need 4 subintervals like they asked. So I'm going to draw 4 lines here. So we're going to go from 0 to 1, 1 to 3, 3 to 6, and 6 to 8. And we want a left Riemann sum, which means I'm going to use my left endpoints as my heights. So let's see, 1340, 1190, 950, and 740. And then we can find the area. So we know that we're just going to do 1 times 1340, 2 times 1190, 3 times 950, and then 2 times 740. And we're going to use our calculator to just add that up for us really fast because I don't want to do it by hand and I don't want you to do it by hand. So 1340, 2 times 1190, 3 times 950. Okay, so we get 8,050. And now we need to think about the units. So I want to go just underneath this really quick. And what we did is the base of each of these rectangles here is going to be the time in hours, right? So the base is time and the height is liters per hour. So we had liters per hour and we multiplied by hours, which means we're left with liters as our final units. Again, this one did not ask you for an explanation, but I'm going to write one underneath just to show you what it would look like. So we need to think about what we measured, and we measured, let's see, the total amount of water removed from the tank during the 8 hours. So the total amount of water removed from the tank during the 8 hours was 8,050 liters. So we measured the total amount of water. It was removed from the tank during those 8 hours, and then it was 8,050 liters. So there's our 3 parts. All right, we have one more. I know this video is getting a little long. Sorry about that. So we have the same problem that we had on the other page with the bananas. All right, so we've still got f of t, which is the rate at which customers remove those bananas. All right, and then f of t is measured in pounds per hour, and t is the number of hours after the store opens. So we're going to be finding the integral from 0 to 2 of f of t dt. So the integral from 0 to 2 of f of t dt. And to do this, we're going to use our calculator, all right? So if we go to math and we pick option number 9, it's going to give us an integral. So we want the integral from 0 to 2 of 10 plus 0.8x sine of x to the third divided by 100. And we want to differentiate with respect to x, and we can go ahead and hit enter. So we get, again, rounding to 3 decimal places, 20.051. And now we need to think about the units that go along with this. So we started with f of t, which is measured in pounds per hour. So we have pounds per hour. And then we had to find the area underneath the curve, and we know that the x-axis is measured in number of hours, which means we multiplied by hours. That gave us our area, which is going to give us a unit of pounds. All right, so this is 20.051 pounds of bananas. And again, you'll notice that this one doesn't necessarily ask you for an explanation, but I want to talk about it anyway because I think it's important for us to make sure we know how to do this explanation. So what did we measure? Well, we were measuring the rate at which customers were removing the bananas, right? And then we found the integral. So what we would say is that customers removed 20.051 pounds of bananas in the first 2 hours after the store opened. So anytime they give us these problems where we have to find an integral, they give us a time frame, right? In this one, it was between 0 and 8 hours. So we had to make sure that we said in our explanation then that this happened during the 8 hours. In this one, they told us that t is the number of hours after the store opened. So to go from 0 to 2 means from the time the store opened to the first 2 hours after it opened. So when we write our explanation here, we want to make sure that we talk about that as well. All right, I know that this was a little bit longer, but hopefully that is going to help us as we move forward in some of these application problems. The units are going to be super important. I will see you guys later. Bye.